So we till now, to in continuation to this lecture series, we have been discussed that we try to define the transducers, and then uh, we try to standardize the transducer term as per the international standard ISA. Then we try to also see that the interrelation between these three terms, transducers, sensors, and actuators, as it is being reciprocated over here. Why the sensor is called the input transducer, or why the actuator is called the output transducers. Okay. What are the additional things you shall be needed to convert a transducer into a sensor? Clear? So you take the second assignment question of the module number 5 from this particular topic, that you try to define these three terms: transducer, sensors, and actuators, and the interrelation among the three. Clear? Then, okay, in continuation to this, uh, in continuation to this, uh, we have been we are now trying to classify the transducers. So the transducers can be classified into 5 standard way. If you are referring the books, then that is normally you will get the 5 standard terminologies, okay, to define the transducers. Whereas, as for me, I have been added another class looking into the new generation of the transducers or sensors, because these are not exactly the same sensor or transducers what we are being used from the past 50, 60 years or 5, 6 decades. Okay. The ages of the mechanical transducers are almost from the 60 years. The ages of the chemical sensors are even from the more than 30 years. But what sensors now you see, it is as good as like a film strip, or the thickness of those sensors are even just little more than the human hair. Those are nothing but it is our smart sensors or the intelligent sensors. Okay? So they are little bit different. So I will brief you, though that is not in your course, but I will give you just a brief snapshot. So very, very interesting the today's lecture is. So the first 5 is the classical way to classify the transducer, that is based on the principle of transductions. As I've been told you, that it is based on the principle of transduction. That means the conversion of one form of energy into the another form. And whenever say in another form, practically it is most of the time always the electrical form of energy. Clear? Either it can be presented in terms of voltage or the current. Be noted, most of the electronic gadgets you use in your day-to-day life at your home or whatever you see, that is all the voltage based. Because the signal conditioning, the output device, the additional add-on circuits are always the voltage most of the time. Number 2 approach can be a primary or secondary transducers. Okay? So it can be a primary type or it can be a secondary type. Okay? So these things you can see. If there is only one transducer which is used to convert the input signal to the electrical signal, then that is called a primary transducer. Or let's say there is a sensor or transducer which is converting a force to displacement, so that is a primary transducer. And then this displacement is again can be converted into the electrical form using one more transducer. If the first transducer is unable to convert it into the electrical form, then you require 2 pairs of transducer, then it is called primary and secondary transducer. In the same way, the same classification can be extended to the another category, that is called primary, secondary, and tertiary transducers. Clear? The third stage. So maximum complexity is the third stage. Rare applications, 2% application. Otherwise, the most of 95% applications are drawn based on one principle only. That is either it is a primary transducer or the secondary transducer. There is another way of classification, that is called the active and passive. So what is active and passive? So if there is any active element like diode like element or any crystal diodes are being used, transistors is being used, then it is an active transducer. If only passive elements are used to design that particular transducer, then that is called your passive transducer. Okay? Analog digital, if any kind of analog, and if it is by default it is always an analog output, but if this analog output is converted into the digital form and the output you are getting response you are getting in the digital, as I even see the digital multimeter, if some conversion ADC devices is already mounted over there, and finally the output you are getting in a digital form, then that is called the digital transducers. Transducers and inverse transducer, this classical definition difference I have been already told you over here. The sensor is the by default which is called the transducer or the input transducer, and actuator is called the output transducer, or in other words the inverse transducer. It gives you the inversion of the transduction principle. That means normally these kind of transducers are used to convert the electrical form of energy into the physical. And the sixth one, what I have been added is that is called the smart or intelligent one. That is the latest one. Yeah. Before that, what are the based on principle when you come about the transduction principle? It can be mostly the thermoelectric principle or the magnetoresistive, electrokinetics, or the optical. These are the four categories, standard categories available. Either it is thermoelectric, magnetoresistive, or the electrokinetics, or the optical. Yeah. So in applications, whether you talk about the industrial applications or the process control is concerned, and another is the embedded. What do you mean by difference between two? Process control is the application of a control system which is used to manufacture the device. So normally it is used in industry. So in industry, you are basically making a product. So for example, you are making a smartphone. So the output of that particular industry is the smartphone. It is the device you are making or manufacturing is the smartphone. So then to that you require a lot of automation is there, and in such scenarios you require uh, a mechanism which is called the process control application. Okay. Now the another class is the embedded control system. So embedded control system is primarily used. Embedded control means that control mechanism is embedded into the device itself. So for example, you are using a smartphone or you are using a smartwatch. So certain kind of control mechanism or automation is done within that particular device itself. So that is embedded into the device. That's why it is called the embedded. Okay. So the device, the control mechanism which is used inside the device, that is embedded control, and that device which is manufactured in a plant, that is called the process. Okay. So I also have certain network issues over here. Is am I audible? I hope you are getting my voice. Yeah. Okay. Thank you, Arman, for your feedback. So these are the things. Okay. As far as the active transducers or the passive transducers are concerned, okay, these have been already used. Normally, these passive transducers are extremely powered because you know that resistance inductive or capacitive device cannot be empowered from the inside. So you always require some battery mechanism or external supply. Without power, they will not work. Okay. Active transducers, no external power supply is required because some kind of power arrangement is already there. You are using some uh, mechanism. Okay, smart accelerometer, vibration sensors, piezoresistive principles, pressure sensor, piezoelectric principles. So any transducers which is designed using these kind of phenomena. Okay, the diaphragm type pressure sensors, silicon diaphragm type pressure sensor, that means made by the silicons. Okay, and remember silicon is the active element. Okay, so semiconductor um, element. So then smart accelerometers, piezoresistive device, piezoelectric device, this falls under the category of the transducers. Okay, so no external supply is required theoretically. Practically, if needed, you can use it additionally. The classifications of the active transducers, uh, the typically what is under your syllabus right now, that is the strain gauge and the LVDT, linear variable differential transducers or transformers we also call. So these two are under your syllabus. But I will give you some brief of and the capacitive transducer. That is one of type of proximity sensors. So proximity sensors means non-touchable. You don't require to touch it to get the output. Okay? So from the bit distance you can take the output. I'll give you some examples also during this lecture series. So that is your analog transducers. Digital transducers, I have been already told you that to convert it into the output, digital output, or the quasi-digital output. Quasi-digital is nothing but it is the pulse. The train of pulses you are getting, that is called the quasi-digital, or the exact digital is the binary output you are getting. Inverse transducers, that I've been already told you. What is a smart sensors now? So a module that containing all the necessary sensing elements which is required and suitably integrated with the necessary electronics, here means signal conditioning device, so that the output is truly or easily compatible with the intended end device. Be noted. What do you mean by that output is truly or easily compatible? That means if you want a reading between 0 to 5 volt at the end, so your sensor should have all the necessary signal conditioning device and the electronics within the same integrated circuit, so that whenever you are going to feed it, you will get your output directly, okay, within the 0 to 5 volt or within 0 to 3 volt. Even now we are not using 5 volt, rather most of the time it is 0 to 3.5. That's all. Okay, so 0 to 3.5 volt, and so that it can directly get the data. Your best example is your pen drive. Whenever your pen drive you fit it, okay, you directly get the data. You don't require anything extra device. Okay, so that is the truly compatible, right? Or easy compatibility. Okay? And this module entirely is formed in a single integrated chip. That is called the smart sensors. And along with these smart sensors, if you are going to add some processing units so that it can process the data and reach to some decisions as well, then that is called intelligent sensors, intelligent devices. Right? So a lot of things you are now heard about as far as the smart city project or smart home projects are concerned. These things are being. So purpose of cutting over here is that, like potentiometer we have been already discussed, synchronous induction potentiometers, these things are not in your syllabus, tachometer is not in your syllabus, accelerometer is not in your syllabus, which have been covered up in these lectures time to time, and those things you can omit or you can bypass from your examination. So from your examination point of view, only three things are important. One is the capacitive type of transducer, one is the strain gauge, and another is the LVDT. That is called the differential transducer for the measurement of motion and displacement. Clear? So for the rest of the period of time, as far as the today's lecture is concerned, we will try to understand how this fundamental sensor is used for the measurement of the displacement purpose. That is called the LVDT. Now, what do you mean by LVDT? It is called linear variable, okay, displacement transducer. It is also called as linear variable differential transformer. Linear variable differential transformer or the displacement transformer, in other words is called. Why it is such a synonyms is there? So basically we use a variable inductance principle, that is change in inductance delta L, okay? And this very principle is used as an instrumentation to measure the distance, okay? So with LVDT is works under the principle of the mutual induction, and thereby it is able to measure the displacement, which is a, or remember, displacement is itself a physical form of energy, right? Displacement is again is a physical form of data. It is not an electrical form of data, and then it is being converted into the electrical energy, right? So that's why this LVDT or linear variable displacement or linear variable differential transformer can be used for the measurement of the displacement. Let's see how it works. That is the construction of the LVDT you see in the left half section of the plane as a figure A. As you see, the motion is given in bidirectional, okay? And there is a core is used. So core is basically made of the soft iron material, which has a very high permeability. Very high permeability. Epsilon is very very high, and then externally it is wounded with the coils, two set of coils. So remember, it is a okay, cut section, the cross sectional view of the figure. I will show you in another dimension also, like this. This is the coil, okay? So the core is inside, is can move in both forward in the reverse direction, in both the direction, and the coil is mounted in the upper side. So you now you can see over here there is a, this is the one set of coil, this is another set of coil, and this is the assembly. Yeah. So this is the primary coil and this is the secondary coil, and the total of set of the secondary coil is divided in two part, half half, and both the side of the primary coil is fixed with the secondary set of coil. Now this is how the connection is being done. Okay, a constant AC supply voltage. Okay, your supply line is AC, so is being provided through over here. So that's why it is mentioned constant AC voltage. That is the input you have given, and from here we are measuring the output. So now how you are measuring the output? You see that one phase is connected in across to the, okay, out through out of the phase. That means both the coils are connected with each other as a out of phase, and then one winding output you are taking over here and one winding output you are taking over here. So that means the direction of flow of the flux over both the side of the secondary coil, that means coil 1 and coil 2, remember that is both are forming the secondary coil together. Okay, and center one is the primary coil. So the direction of flow of the flux in both the coil are opposite in direction. If one is moving in the forward direction, another moving in different reverse direction. And in the, once the phase will be shifted AC across the AC voltage after 180 degree, then what will happen? The direction of flux of the coil 1 and coil 2 again will change. So therefore across this particular output you will always get the differential voltage. So this differential voltage is either minus V1 plus V2 or it is plus V1 minus V2. Okay? So this black line what you see, that is the insulations. And this is the, you can say that the electrical equivalent circuit of this mechanical diagram, of this physical diagram. This is shown that how, see, this is the phase reversal you are getting. Okay, so this coil is not directly connected here. If this connected coil is connected through here, so that is in phase. This coil's external end is connected to the internal end of the another coil, so that is out of phase. So that's why you are getting the differential. I hope that now you are able to understand. Okay, just surrounded. So it is a cylindrical former which is surrounded. One end is the primary winding in the center of the former and the two secondary windings at the side. Yeah, and this core is primarily is a made of a, okay, high permeability. This is the high permeability magnetic shield. So what is the advantage of high permeability magnetic shield? So that the external magnetic field in the surrounding area cannot disturb it. So that means whatever reading you are getting, that is very very reliable and highly efficient reading. Okay, very accurate reading you will get. Fine. And then this housing what you have done, it is made of the stainless steel. It is mentioned over stainless steel housing and the end caps. Okay, which doesn't allow any external ingredient to flow through it. And this stainless steel housing is primarily used to form your primary winding in the side and the secondary winding in the primary winding in the center and the secondary pair of two secondary winding in both the sides. And this core is actually made of high density glass filled polymer coil form. Okay, so which give you very very high degree. Now I have that these things you have been understand that why you will get the differential voltage. This is the reason. So if you now compare with the standard nomenclature, ideally it can compare with the transducers, transformers nomenclature also. Okay, in transformer also we have a two set of winding, primary and secondary winding, but not in this form. There is only one primary and one secondary. So that's why it is also sometimes called the differential transformer or differential transducer or the displacement transducer. All the three names are okay. Okay, that is how the it works. Clear? So now how it works, let's see. We are considering the three cases. One, I am assuming that this core is fall exactly center of the coil, exactly at the center. Clear? So if it is exactly center of the coil, core is exactly mounted over here, then up to what degree it is going to cross the secondary windings, there is hardly any chance, right? So if, because of this, what happened, if the core is remained at the null position means at the center of the axis, okay, then it will not provide any momentum, and therefore the induced voltage in the secondary winding will be in the both side, either it is zero or is the equal. So if it is equal, if V1 is equal to V2, in that case what happened, V1 minus V2 is equal to 0, and the net output you are getting 0. So that means no E output, that means the induced output you will get in this condition. Now let's say the case number 2, where we are assuming that the core is shifting in the left side of the cylindrical position. Okay, in this cylindrical position you see, the core is moving in the left side of the coil. So if it is left side of the coil, so in that case what will happen, that because of the coil, this one, okay, secondary coil number one, the E1 will be very high because the induced voltage will be very high, whereas the coil number two there is a no core, so there is a no induction, so E2 is reducing, either it is tending to zero. Clear? So in that case, you will get the maximum output due to the 1. So now because of that, because core is moving in the left half side, so E1 is increasing, E2 is reducing. The final output is you will get the maximum E1 and E2 is equal to 0. So in that case, E out is equal to nearly equal to E1 or it is exactly equal to E1. Okay? Okay. So the electromotive force voltage induced in the secondary coil is greater when you are comparing with the secondary coil. That is how the case number 2. We consider the case number 3, last case. If you are saying that the external force is motivating this core to move from left to right. In the earlier case, case 2, it is moving from right to left. So in case 3, if it is moving left to right position, okay. So in that case, what happened in the same scenario, E2 is increasing and E1 is reducing. So net output you will get because of E2 minus E1. Okay. So this thing is indicating what electrical output you are getting or not. If they are getting no output, so that means displacement of the core is 0 and it is exactly over the primary side. Okay, it is falling influence to the primary side, and once it is started influencing from the secondary side of any of the coil 1 and 2, so whether the positive value of E1 or E2 will decide at what direction core is moving. Okay, so you are not only able to measure the displacement, okay, and it is very precise measurement. You can get the range in the millions also, 10 raised to minus 3 unit, very accurately, but also you are getting the direction also. So these two classical advantage, it is a primarily a mechanical or physical transducer, okay, but it's a in the resolution is infinite, very high. Okay, one of the most robust transducers still we use in our life, in your day-to-day life, particularly in industries and in your experimentation purpose from the past 5-6 decades or even more. So theoretically the resolution is infinite, very high output. It gives you the uh, very high sensitivity. Okay, it gives you very linear curve. I will show you ruggedness. Why it is ruggedness? Because the external field cannot be influenced the inside reading. Very low hysteresis rate. Okay, less frictions and the low power consumption. So it has all the important ingredients as it's a parameter, so that why you should use in the field environment or in the external field environment, or why it is so popular in the industry. Okay. So as far as the displacement measurement is concerned, as a primary transducer, most of the time it is a number one choice because of the robustness and high resolution as far as particularly industry application is concerned. Not only that, the uh, it will also give you the directions as well. Okay, direction measurement also. Okay, it will give you the displacement and measurement also in the direction, that in which direction the displacement is occurring. Okay, in the forward direction or in the reverse direction. Input can be a weight, can be a pressure, can be a force, can be a acceleration. Okay, so all the variable pressures can be given, and finally to convert it into the displacement form. So LVDT can also be used as a secondary transducer, can be used as a primary transducer. As a secondary transducer, it has the widest range of applications. Clear? What is the limitation? Resolution is very high, but it is not very sensitive, and it is excited with only AC supplies only. That you have to make sure that with the help of simple batteries or lithium-ion batteries or fuel cell, you cannot keep it. Okay? So DC supply won't work. You required some AC supply mechanism, and the okay, frequency range can be varied right from the 50 hertz to 20 kilohertz excitations. Okay? So this is the limitation. The minimum should be 50 hertz, and the maximally can be 20 kilohertz, not more than that. That means for the megahertz range, it can't. This is the theoretical characteristic what you see. Okay, why you are getting this difference, this null position difference, this characteristic should be over exactly over here. Remember that is a E output, which is the difference between either E1 minus E2 or E2 minus E1 when we are comparing with the character. That means in the what you call the transfer characteristics is concerned. Okay, so as far as these characteristic lines are concerned, the vertical axis is the magnitude of the differential AC output, and this will give you the null balance positions. So, as far as the LVDT characteristic is concerned, one of the very important aspect you see, whether you move from this particular 0 point, we are assuming that if your core is falling exactly on the center of the binding, in that particular case, if this particular point is 0, and we are considering that in the right and left half of the point, the final ultimate unit is minus 100 or plus 100. So this is minus 100 or plus 100 is not the voltage or the displacement, but this is the unit. So this plus or minus 100 you can divide it in any count. Now, let's see. So what exactly happened? This V should curve exactly fall over this particular center point, null point where it is mentioned. Okay? But what you see in this red line, this is the real characteristic of the transducers, where it is starting from little above than this null position, 0. Why it is occurring? Because it is influenced through the magnetic field. Okay, and in this particular scenario, if you are going to count this particular course, as far um as the core assembly is concerned, okay, uh, as far as the core assembly is concerned, so which is made of some kind of nickel iron high permeability of materials. So you see that whenever this charging or discharging phenomena occurs, it always takes some time to reach to the 0 position. Okay? Because the permeability is not infinite. So because of this, what will happen? There will always be some induced voltage over here. Cannot be a 0 if you consider the charging and discharging phenomena. So that is the reason that why you are never able to achieve the null position, and this is the error you are measuring or you are getting as far as whenever you are going to measure the here. That is the only disadvantage you can say, that this it is not exactly the characteristic is not able to reach the null position difference. So the practically if you are going to draw, so this characteristic will come something like this. And then the perfect linear will go in this characteristic. Okay, yes. Now, as far as this phase reversal, that means if you see the output difference is over here 90 degree. This slot you can be linearized by using a phase shifting element. So you apply a phase shifter device, so this characteristic can be increased. So right now for the 90 degree what linearity you are getting, for the exact 100 degree, if you are get a phase reversal in the left half side or the right half side, so in that case what happens, the characteristic will be drawn in this way or the characteristic can be drawn in this way. So you can increase the linearity of your characteristic. That additional arrangement you have to do. Otherwise, this is the classical way how the LVDT is used for the displacement purpose. So with this, I'm winding up the today's lecture. Tomorrow we shall be meeting at 11 o'clock, and we are going to consider our new topic, that is the strain gauge. Till then,